So I want to tell you the story of Alice and Bob, who saw at some amusement fair this strange sign of a lottery that claims that you can actually check that it's fair. So they go into to investigate, but on the face of it, it's a very simple thing. It's about it looks almost like a simple coin toss. So the rules are very simple. So you pay €1 and you get a ticket. So here's what the tickets look like. And they're actually scratch cards, right? So they're the covered fields, and then you scratch them open, and then you get two symbols, right? So the only symbol that ever appear, you can see here, it's a cross or a circle. The payoff is very simple, so that actually you could say that equal symbols win. So here's the winning table. And so you can see it looks like a fair lottery. And so actually if the tickets are generated with a random generator that with equal probability puts crosses and circles, then this is a fair lottery, clearly. Right? It's exactly a coin toss. So one way to make this verifiably fair is to allow the people who want to play a bucket full of such tickets so they can test and see whether it's fair. Right? So that would be too easy, a little bit too easy. So we have the kind of verification that this lottery is offering you is a bit more complicated. I need this kind of complication to explain what I want. So just bear with me to explain how it works. So actually for checking, so for the verifiable stuff, the tickets have to be looked at also from the reverse side. So now here is the reverse side of the tickets, and they're also scratch cards, right? So you have 4 fields that you could potentially scratch. But actually, if you do it on one side, so let's say on the Alice side, on the A side, you scratch one of the fields, then the other one becomes unusable, as you can see here. So it's just you can't read the other side. So actually here the fields would be called the win A, win B, test A, test B field. W A T A and so on. Right? So in the following to just as a shorthand for these fields. Now the basic testing rule is very simple. So for testing, you can open any pair of fields. Except the combination with which you would actually play the lottery in the end, except the win A, win B combination, right? So that's the one that you actually use for playing, and all the others you can check. So the allowed tests, just to give a complete list here, would be the test A, win B, like that, or the win A, test B, like that, or the test A, test B, like that. So these are the possible combinations that you're allowed to check. And now, of course, the checking works like that. You get a bucket full of tickets, and then you just go and open some of these combinations, and you take the statistics for each of these cases and see how often you get the same symbol or different symbols, or which symbols actually. The same or different is really the theme that you're looking for. Okay, so now we have to look at what you can conclude from the statistics, because of course you want to, after checking doing all this checking, you would like to learn something about how fair the lottery is. That's the whole point. So we have to go through this analysis, how to get from the numbers that you obtain here to the one that you're interested in. So the assumption of this analysis It's a very natural one in this context. I mean, we are at a lottery, amusement park, so, and the way scratch cards are made is that you first print the symbol that is later then uncovered, right? So the symbols are ink on paper. By which I mean in particular, they are fixed beforehand and they do not change by scratching. Right? So that is certainly a natural thing to assume. Now, then to go forward with the analysis, we want to estimate how many losing tickets there might be, right? And so let's look at a list of losing tickets. Losing tickets are those where the win A and the win B field have different values, right? So then you lose. And so list of losing tickets. And this would be 8 different ones. And I just write the important one set of them. So for simplicity, the win A side we just fixed to be a cross. And of course, there's the whole thing again with when the win A side is a circle. Okay, so here are the losing tickets. So these are the losing tickets, and these are the possible tests we can make. So now we can check in this table which test would detect a flaw, that is, a disagreement of symbols. So, for example, let's take the tests where we take the win B test A combination, and we have this kind of losing ticket, then yes, that would be detected. You see different symbols if you make that test. And the same would hold for this one, right? And the same would hold for this one. And also, with this last kind of losing tickets, actually all tests would detect it, right? So now, how many detections do we get? For each kind of losing ticket, at least one test will detect it, and in this case it's even better, right? So a third of the tests would actually detect the losing ticket, and so let's go on with that. So the number of losing tickets must be less than 3 times the number of observed disagreements. This is an inequality, so it's an underestimate. It's not an equality, and it's an inequality. So sometimes this could be properly larger for 2 reasons. One is that sometimes more tests actually detect the losing ticket, like all tests would detect one kind of losing ticket, but also that winning tickets sometimes produce disagreements, because if there could be equal two disagreements on the way. This is the central estimate of the argument. And so maybe it also helps to recap what happens in this table in a slightly different language. So we are comparing these symbols. And so, for example, asking whether this is equal to the test B side. This is an allowed test, right? Another allowed test is the one of the 2 test sides. And another allowed test is the one with a win B side. So these are actually the 3 allowed tests, right? And you ask whether you find agreement or not. Now, a losing ticket is simply one that has the outer sides different, right? So that means that at least one of the 3 places you have to have disagreement. This is the number 3. So the number 3 just corresponds to these 3 comparisons. One of them has to be a disagreement. There's also another extreme case that it maybe helps a little bit to look at. That is, what if there are no observed disagreements? No observed disagreements mean that we always find agreement. Now, this is basically nothing else but a statistical test of the hypothesis that all the symbols are always the same, right? There might be all crosses or all circles, but they're always the same. The way to test that is make all these comparisons. And if you always find agreement, you find your hypothesis verified, and then you conclude that also here you have to have, on the outside, you also have to have agreement. Like all equal symbols means all equal symbols. So then you would have no losing tickets. That's the case where this is 0 and this is also 0, then necessarily. Right? This is the basic argumentation for this inequality. So the next thing, of course, is to see how this plays out in the data in the story. Right? I didn't give you those data yet, but the story comes with a particular set of findings. So let's consider those. Okay, so with these numbers, you see that in all the three comparisons, we get 15% disagreements. These numbers are all equal, but that's an accident. It doesn't really matter. They could be different for the argument. That's not important. Just makes it simpler. So this is the number of disagreements that we see, the rest from 85%, and 3 times that is 45%. So this is an inequality. So the number of losing tickets is less than 45%, which means that here we have 55%. Now that's great, right? Because for Alice it means that she's actually winning. Right? It's not 50-50, it's 55% winning. And so actually if you just reconsider what she's paying and how much she gets, so that means like it's a 10-cent gain per ticket, right? That's nice, isn't it? So the lottery isn't that exactly fair. It's actually rigged in favor of the player. Now, once Alice realizes that, of course, she takes all the cash she has with her and buys lots of tickets, and so brings them in and does the scratching. But to her horror, she finds quite different numbers, namely this one. So 15% is what she actually finds. Now, if you convert that to money, that basically means that she doesn't have a 10% gain per ticket. She has a 70% loss. That's pretty bad, right? So naturally, she feels tricked, and though we have to find out what happens, right? What happened? Of course, you have to go through this argument. And actually, the argument that I gave is perfectly good for printed symbols on paper. So what else could it be, right? If not printed symbols? What else could it be, right? So maybe the tickets actually contain some internal mechanism. So like a smart card, right? So if not symbols, maybe smart card, something with a chip in it, right? Smart cards. And the idea would be that so once you scratch one of the symbols, there's more happening than just the opening of the symbol. The other symbols on the other side get automatically changed in agreement with what the lottery people want, right? So there would be like a wiring between the two halves of the ticket. And so if you find a cross like here, then actually the other two symbols are generated on that occasion in a random way, in such a way that the statistics matches up. Right? So this is what I described. This is perfectly possible. You can just arrange the rules for this random selection of other symbols that are written on that in that moment that would do exactly this kind of statistics. So the key element of this smart card here is the wire that goes from the A side to the B side. And of course, it would also do it in the other direction because nobody told us which one to open first. Right? So it would have to be like both two ways active. Right? So Alice concludes. There must be communication. So some signal has to go from the A side to the B side when you scratch the first symbol or on the A side and conversely, right? So that's a reasonable hypothesis, and actually, yes, it would be possible to produce such tickets. Then this whole analysis where you have printed symbols on paper would of course be wrong because something actively happens on the moment when you scratch. So, okay, Alice and Bob, her friend Bob, they're physicists, so they try it, right? So here goes. So they have, they buy a big batch of tickets, and they actually mark the tickets so that later they know how the pieces fit together. But they mark both sides, but they cut them up and take them to distant locations. So Alice takes all the A sides and Bob takes all the B sides in their own buckets. They each have a number now, so that we know which one corresponds to which. And so Bob takes them on a long trip. Right? Takes to another continent, if you like, to another planet or whatever, far away, goes into a basement, in a Faraday cage. Every known physical interaction is cut between the two, right? And as best as you can do in any lab. So now they're separated, and they start opening their tickets, and each of course still has a win and a test side. So they make a choice, and they do their scratching, note the results, right? And now after having all these results, they bring them together and do the same statistics as before, right? And so what do they find? According to this theory that maybe there are smart cards involved, according to this theory, the correlations should be gone or different from what they find. But no, they find the same correlations. So I think the only conclusion from that, the communication is not what drives these tickets, right? So there was no communication. That you can find by just doing this experiment, right? Cutting up the tickets and cutting any known physical interaction between the two. And still, it's the same. So that was not the point. So what else? So how were the tickets made? Alice and Bob go to the people running the lottery, and they still feel tricked, right? So they want to know what did you do to us? How do you make these tickets? And so they only get a very short answer, which is, we just use entangled particles, So they go to their friends who operate a quantum lab in Singapore, or actually in many other places in the world. We have such labs where indeed such statistics are commonplace. So in the quantum lab, what you would do, you would have a source of entangled photons, for example. Any kind of particles will basically do. Entanglement is a special kind of quantum correlation. And because it's just correlation, it is really talking about separated particles, right? So afterwards you can separate everything. That's why the cutting of the tickets didn't make any difference, right? So this is just mere correlation, quantum correlation to be sure, but it's just a kind of correlation that quantum physics has for us, right? So then what would the tickets do, right? So if you start scratching one side, that would make one of two possible measurements. And they exclude each other, actually, also physically. So in physics, you cannot put a polarizer both in this orientation and in that orientation at the same time. but that is the sort of thing that you would need. So they're exclusive measurements, which explains the feature of the tickets that if you scratch one side, you lose the information on the other side. That's actually a typical feature of quantum mechanics. So you have these two possibilities of what you can look at for these two particles, and that's the kind of statistic that you get. Actually, quantum mechanics does not allow you to get like no disagreements at all on these tests, like every agreement but complete disagreement on top. That is something that quantum mechanics doesn't allow, right? So there is an inequality called Sirisson's inequality, and so the 15% here are possible because the lowest you could get here is something like 14.6 something, which is which is 2 minus square root of 2 divided by 4 or something like that. So there's a number that you can compute. This is the version of Sirisson's bound for quantum correlation. So 15% are actually in the realistic range. So that is indeed, quantum physics allows you exactly the numbers that I was talking about all the time. So what do we conclude from this lottery about physics? Well, think of Alice's assumption in the big analysis, probabilistic analysis. The assumption was that the tickets are something like ink on paper, that there is some information there, and the scratching, which in physical terms would be the measurement, just uncovers something that is already there. So this is clearly the classical notion of measurement. There is something, and then we just detect that. So, but it's a fact that is given independently of whether I choose to scratch open one of the fields or not, right? So one thing that we do learn from this lottery about physics directly is that measurements do more than simply uncovering a previously known fact. So there's always an interaction between the measurement apparatus and the quantum system, and in this interaction, the result is generated. So it's not that a measurement simply just looks and it's something that is there, that was there before and is there after. If you make that kind of assumption, you get wrong results in certain experiments.